Alright, so in this problem, we are given a frame that has an external force of 2,000 newtons being applied at the center of member BC, and it's going in a negative y direction. We are also given that the frame is supported at 2 points. At point C, it's supported with a pin joint, and at point A is supported with a pin joint. All right. So in this problem here, you have and then the two members AB and BC are connected by an internal pin or pin at point B. All right. So if we look at just if you treat this I guess this frame ABC as a single rigid body, it has four unknowns. It has AX, it has AY, and then it has CX, and it has CY. Right? So they have four unknowns in this problem, and we only have three equilibrium equations. All right, so we can't solve it. We can't solve it as drawing like a single rigid body. So what we can do is we can treat it as two separate rigid bodies. Okay, so we're going to break this into two systems. All right, the first system, all right, is we'll look at member AB. All right, so if we look at member AB, we have at point B we have a pin, and at point A we have a pin. So we know that it's drawn at a 60-degree angle. We know the length is equal to 3 meters. So we know that at point A we will have AY and AX due to the pin, and at point B we will have BX and BY. Right? So those are the internal forces due to the pin at B. So what we're left with here is, or what we'll notice, I should say, is that what we have, our forces are only applied at 2 points. All right. So when you have forces that are applied at only 2 points, what you could draw this as, or this instrument as, is you can draw this as two forces. All right. You could draw it as force B, all right, and force A. All right. So since force B and force A are both going through, or are both applied at a single point, and there's only two forces being are acting on member AB, we can define member AB as a two-force member. All right. So since AB is a two-force member, all right, we can so since AB is a two-force member, all right, we know the following two things. We have the forces at both ends will be, so A, the magnitude of A will equal the magnitude of vector B. The direction of A will be opposite of the force at B, and that the direction, or the force direction A and force direction B will go through points A and B. All right. So essentially what this simplifies down to is that member AB will have two forces, B and A. All right. And those two forces will be at a 60-degree angle relative to the x-axis. Right? Or they go along member AB. Right? We talked about this a little bit in chapter 5. So we're just applying that knowledge to this problem here. Okay? So the reason this is important is that it'll simplify our analysis of our our frame here. So what we can now do is we're going to draw a free body diagram of member BC. Right. So if we draw member BC, right, we know that we will have a force at B. All right, that force at B would be equal to, is going to be at a 60-degree angle with the negative x-axis. 2 meters away from B, we have a 2,000 Newton force that's being applied down. And then at C, at point C, which is 2 meters away from here, all right, we have C of y and C of x. So those are the two reactions at the pin joint. All right. So now that our free body diagram is complete, what we can do is we can determine our three unknowns. So we want to find B, Cy, and Cx. Right. So to do that, we will just apply our equilibrium equations. All right. So the first thing we can do is we can sum our moment about point C and set that equal to 0. You could also sum the moment about point B. That would also, you could also then solve for Cy with that method, but we're going to sum the moment about point C. So if we do that, we'll end up getting plus 2,000 newtons times 2 meters plus the magnitude of force B times the 4 meters times the sine of 120 degrees. All right, so this is just FD sine theta. If we use the right-hand rule from point C to point B, and then from point B along the direction of our force, we would get a positive moment. So if we solve for B, in this case, what we'll end up getting is we'll get minus 4,000 Newton meters divided by 4 meters times the sine of 120 degrees. If we get that, we'll end up getting 2,000 over radical 3 newtons, which is approximately 1,150 newtons. All right. So, so with that, we can now use our remaining equilibrium equations to find Cx and Cy. So if we just sum all of our forces in the y direction and set that equal to 0, we'll end up getting, and this should be a negative, this should be a negative number here. Right. Sorry. So force B should be a negative number. And then at okay. So for then we could sum all the forces in the y direction, set that equal to 0. So we would get minus 1,150 150 newtons times the sine of 60 degrees. We'll include a negative sign based off of our diagram here. So sine of 60 degrees is radical 3 over 2. Alright, minus 2,000 newtons plus Cy. So we'll end up getting C of y is going to be equal to 2,000 newtons minus 1,000 newtons. So it's going to be equal to 1,000 newtons. Alright, and then the last step of our problem is to sum all the forces in the x direction and set that equal to 0. Alright, so in the x direction we only have c of x, and then we have minus b cosine of 60 degrees. So if we'll see that c of x is going to be equal to b cosine of 60 degrees is 1/2. Alright, so if you plug in b as being equal to minus 1,150 newtons, alright, we'll end up getting 1,150 over 1/2, or we'll get minus 577 newtons. Alright, and that concludes this problem. So we were able to if we go back here, just to recap what we did, is we broke our rigid body into two parts. Our first thing we did was we separated our frame into two parts. We looked at AB first, and then we looked at so from AB we determined that AB was a two-force member. Alright, and then using that knowledge we were able to then draw a free body diagram of BC. Alright, and once we had our free body diagram of BC, we could say that we could then find C of x and C of y using our equilibrium equations. Alright, that concludes this example problem on analyzing frames.